Okay, so again, with symmetry, we can assume that if it took 1.53 seconds to go to the peak, that it's going to be 1.53 seconds to come back down. If I wanted to prove that, what I would say is I want to analyze kind of the second half of the flight. So if it took 1.53 seconds to go to the peak, now what I'm saying is I'm up at 11.5 meters, and I want to figure out how long it takes to fall to the ground. So this is a drop from rest problem. We've done this, right? And if I want to know how long it takes, I want to go to the position equation. And I'm trying to find time, okay? So what I want to know is how much time passes to get back to position 0. So I want to set this equation equal to 0. Half the acceleration is going to be negative 4.9 meters per second squared. I don't know time. That's what I'm trying to figure out. I want to know the time that it takes to get back to position 0. If I'm analyzing the second half of the flight, the starting velocity at the peak is 0. So again, this term goes away in this sort of problem because V0 is 0 meters per second if I'm just analyzing the second half of the flight. And then Y0 is the Y position at time 0, or that starting height. So I have what I need to solve for T, right? I would subtract 11.5 from both sides. And I'll keep the units on here and just see how that works out. So that would take care of that term. Then I would need to divide through by negative 4.9 meters per second squared, both sides. I'll put an extra digit on there. That would cancel that term. And then I would need to take the square root to solve for T. And if you do that, you do find that the time is 1.53 seconds. So it matches what we expected, just due to symmetry. If you do track the units, we've got meters over meters per second squared. The meters would cancel. We would have per second squared in the denominator of the denominator. So it would flip, and you would end up with units of seconds if you carry through the units. All right. So that's not so much necessary as just a confirmation of what we thought, that it would take 1.53 seconds. Now, what I want to know is up here, the velocity was 0. What is that downward velocity after it has fallen 1.53 seconds? So if I go to my velocity equation, now I don't know the velocity. I'm trying to find the velocity. If I'm accelerating at negative 9.8 meters per second, I do know the time I'm interested in is 1.53 seconds worth of falling. And the starting velocity, if I'm just analyzing the second half, is 0 meters per second. So to find the velocity when t equals 1.53 seconds after the peak, I just need to multiply these two together. Seconds will cancel seconds squared. And you should find that the velocity is negative 15 meters per second, which matches the launch speed. It's just downward at this point. Yeah.
So for that problem, the equation that I set up was negative 9.8 times 3.06 plus 15. And I still got negative 15.
Yep.
So is that always going to work? Or
Yeah, so it will. What you did is you analyzed the entire flight time, right? So if you analyze the entire flight time, the starting velocity is going to be that positive 15. The time would be 3.06. So that is a correct way to analyze it. Yep. So that's another way of solving this. I'll jot that down because you probably didn't hear it in the video. If we analyze the entire flight time, now that we know the entire flight time is 1.53 seconds plus 1.53 seconds, 3.06 seconds, the trick here would be if I'm analyzing the full flight time, my initial velocity is positive 15 meters per second. And you will get the same answer. Yep, I'm glad you asked that question. It's a perfectly valid way to solve that. Again, due to symmetry, that's what we expected, right? If it's 15 meters per second of launch upward, the downward speed at catch should be the same. Okay. Now, this is kind of wordy. What we did kind of in the first part of this is to break the motion into the up motion and the down motion. There's a way we could do that, kind of like we were just saying with velocity. If I want to analyze the entire flight time, if I go to my position equation, what I'm saying here is my initial position is 0 meters. My final position that I'm interested in is also 0 meters. Half of g for the t squared term. I'm going to run out of room if I include units, so I'm just going to leave it as without units. The units would be meters per second per second. And then here, if I'm analyzing the entire flight time, I do want to keep that 15 meters per second in the V0 term. So one way I could solve this, first of all, the 0 meters just goes away. I don't need to include it so much. I could factor out a t from this term and this term. So going back to your basic algebra, right? If I factor out a t from the first term, it's going to be negative 4.9t. I've got to factor out a t from 15t. And this all equals 0. So there are really two solutions here. Either this t equals 0, right? Or the quantity here inside the parentheses must equal 0. So the first solution is true at launch. At launch, when t equals 0, you're at a height of 0, right? The other solution is going to take care of when you get back to 0. Okay. So doing my algebra here, I would subtract 15. That would be 15 meters per second if you're tracking units. That goes away. Divide by negative 4.9. That isolates t. And if you take 15 divided by negative 4.9, you do get 3.06 seconds, which we already proved kind of in the double analysis. We said that half the flight time was 1.53 seconds. The second half of the flight time was 1.53 seconds. We add those up, we get to that point. So it's really a matter of preference on some of these, whether you want to break it up into the first half of the flight and the second half of the flight. You do have to be careful. In order to say those two quantities are equal, you do need to have the special case where you launch at height 0 and you land at height 0. If it's kind of an unbalanced launch, so like if you throw something up off a cliff and then it ends up in the canyon below, this method wouldn't work. Your two halves of the flight would not be equal necessarily. Okay. All right, we are almost out of time. Stop my recording here.